one potential issue with these machine learning models, especially if the models are more complex or the data set is smaller, is that, as I mentioned on the data issue section of this presentation, is that the models can sometimes just memorize the sample IDs, like learn the sampling error, or learn batch effects and confounders, and not really learn the biology, not really learn a generalizable pattern, the signal in the data. And we don't want to rely on a model and then believe that it's doing well and then deploy for clinical use or for downstream application in biology, and then realize that the model was doing completely wrong predictions. So while we are developing the model, there are best practices recommended in machine learning that allows us to quantify, mitigate, and test those models, those potential issues in the model. And one is the data splitting, where we split the data into training, validation, and test sets to check whether a model is learning real patterns in the data instead of just memorizing the data set. So the training set is used to fit the model parameters. The validation set is used while you are testing, you're training multiple models, and then you want to evaluate which one is doing better. And then you want to adjust other hyperparameters in the model, like hyperparameters that are parameters that are not learned during training, like regularization weights or regularization alpha. Or if you're testing different model complexities, you want to use the validation set separated from your training set to choose the one that is overfitting less than the others. So the one that gives the best validation accuracy instead of the one that gives the best training accuracy. But if you use both of them like that, they are not fully independent anymore, because your model is kind of indirectly seeing this subset of data. So the best practices recommend that at the beginning of your setup of your machine learning workflow, you also put aside a test set. So the test set, it's kept completely untouched until the very end of your machine learning workflow. After you choose your model, you're not changing your model anymore. Then you can test the final generalization performance of your model. If your model, after doing training and validation, picking the best model, and then it does well on this test set, then you can be more confident that this model is generalizable. You're kind of emulating the way that an end user would download your model, preprocess their own data set, and then test your model on their new data set. So that user would not change your model, they would just apply your model on this new data. So that's what you're simulating here. This is what happens more often, but the ideal scenario, if we have enough data, would be to have our data set split only on training and validation set, the same way we do here. But then we would reach to another lab, to somebody else's data set, and acquire that data set that has the same type of features and outcomes and covariates to test our model on data that was collected by other people in another lab. So we can eliminate potential data leakage or potential bias that comes from this data. That would give us a lot more realistic estimation of how our model would perform on the real world, on a real application. And if machine learning models have the opportunity to cheat, to get a shortcut to make an accurate prediction instead of doing the hard work of learning through biology, they will do it. They will cheat. So you have to be very careful about data leakage. For example, if you apply dimensionality reduction on your entire data set, or scaling, you fit a scaler to do scaling on your data set, on the entire data set, then it's possible that the model will leverage that, the variation that was introduced by that approach to make a good prediction instead of learning the actual biology. So the advice, the best practice in machine learning is to split your data set first, and then you apply any transformations, any fitting, like dimensionality reduction, fitting or scaling fitting on your training set. And then after you fit any or imputation on your training set, after you fit your imputation model, your dimensionality reduction model, your scaling model, then you apply that transformation to the validation and test set instead of fitting on the entire data and applying on the entire data. And I just wanted to clarify some terminology issues in the literature. If you are interested in reading books and papers about machine learning and about machine learning applied on a clinical biological context, the terms validation and test are used very inconsistently. For example, many studies will call this test set in a trained test split, and then they will call this independent validation. So you gotta be careful and read what they mean by validation and what they mean by testing. And I just wanted to clarify some terminology issues that you may find in the literature. If you start to read different books and manuscripts on the topic of machine learning in general, or machine learning applied to biomedical sciences, the terms the terms validation and test sets can be swapped. So sometimes you will see somebody referring to validation as test set and the test set as validation. Uh, the logic is the same, it's just that the names are swapped, and they are not wrong. They're different researchers, different fields came up with different nomenclature. You just have to read what they mean when they are using those different terminologies. Also, specifically in biomedical machine learning, they have other terms that you may find. They will have, for example, a exploratory cohort, which is a very small set of data that they use to do some exploratory analysis, some preliminary analysis. After that, they will have a discovery cohort, where is the cohort where they will apply the machine learning. They will develop the machine learning model. Like here, for example, in this study, they compared, they did like a train cross validation. They are calling it train validation split, and they tested lasso, logistic regression, random forest, support vector machine, and XGBoost. They did like a benchmark. So they compared, they did like a training validation split, and they compare the models and pick the best, and they tweak the model using that. Then they use an independent test set here that they call multi-center validation and robustness validation, another independent test set. So you see that the names can change completely, so you just need to be aware of that. It can be confusing sometimes. Another example here is this other paper where they call it discovery phase, where they collect data and do preliminary analysis, and then the validation phase, where they validate biomarkers that they discover doing statistical analysis, and then pathway perturbations when they go to do an intervention. So there are different uses of the word discovery, validation, train, test. Yeah, it can be a little bit confusing.